Welcome to the Explainer. Today, we're exploring a massive leap in clean energy technology. We're talking about pulling our most valuable, versatile fuel literally directly out of thin air. I know, it sounds a bit like science fiction, but as you'll see, it's rapidly becoming science fact.
We've got a really fascinating journey ahead of us today. We're going to cover the green hydrogen paradox, splitting thin air, the VC funding boom, atmospheric space mining, and finally, our elemental future. Let's just jump right in.
Section 1. The Green Hydrogen Paradox. Let's dive into this by looking at the absolute biggest roadblock we currently face when it comes to creating truly green hydrogen fuel right here on Earth.
So, hydrogen is often hailed as the ultimate clean energy carrier, right? But to actually make green hydrogen, you generally need two things. You need highly pure fresh water, and you need abundant renewable energy to split that water into hydrogen and oxygen. But here's the massive geographical dilemma we run into. The places on our planet with the most abundant solar and wind energy are usually the exact same places with the absolute least amount of water.
And this really brilliantly illustrates that exact problem. When you look at it globally, notice how the regions of highest water risk perfectly overlap with the areas of highest solar and wind potential. We're talking about places like North Africa, Central Asia, the Middle East, and Central Australia. To generate green hydrogen at scale, using traditional methods, we'd essentially have to pump highly purified water straight into the middle of the desert. And honestly, that's just incredibly expensive and a logistical nightmare.
Which brings us to Section 2, splitting thin air. Researchers at RMIT University looked at this problem and asked a pretty brilliant question. What if we could just bypass liquid water entirely? Their solution is a technology called direct air electrolysis, or DAE for short. Instead of pumping in liquid water, this system essentially acts like a giant chemical sponge, drinking moisture directly out of the ambient atmosphere. Think of it kind of like those little silica gel packets you find in shoeboxes, but, engineered to power human civilization. Keep in mind, at any given moment, there are roughly 12.9 trillion tons of water suspended in the air. That is an enormous, untapped resource. Mechanically, inside the core of the DAE module, there's a porous medium. Think something like a melamine sponge or specialized glass foam. This sponge is soaked in a highly deliquescent substance, like sulfuric acid or potassium hydroxide. Now, these are chemicals that naturally want to absorb moisture. Because of this, the sponge continuously pulls in water vapor from the air, even when the air is bone dry. We're talking perfectly functional at just 4% relative humidity. It's wild. So here's how this actually builds into fuel production. First, the sponge captures the vapor from the air. Next, it acts as a capillary network, transporting that newly captured liquid water outward to isolated electrodes on either side. Finally, a renewable power source, like a solar panel, sends a current through those electrodes, splitting the water into highly pure hydrogen and oxygen gases. And because the sponge acts as a physical barrier, those gases never mix. That actually solves a major purity issue that has plagued older vapor-fed systems. Now, the absolutely crucial point here is that this isn't just some hypothetical lab trick. The RMIT team tested this outdoors, driven entirely by solar panels. The performance highlights are absolutely staggering. It ran for 12 consecutive days of perfectly stable operation with zero liquid water input. It operated at an incredibly high 95% Faradaic efficiency, producing 745 liters of hydrogen per day per square meter of cathode. And because electrolytes like sulfuric acid have super low freezing points, this module can even operate in sub-zero temperatures. It's a highly viable, scalable solution for the world's most arid environments.
Moving on to Section 3, the VC funding boom. With breakthroughs like this proving that the historical geographical constraints on hydrogen are kind of disappearing, the financial world is taking serious notice. To put that into perspective for you, in just the first 4 months of 2024 alone, venture capitalists poured over $1 billion into startups developing low-emission hydrogen technology. That is more than 2/3 of the total raised in all of 2023, packed into just a single quarter.
We are literally watching a green gold rush unfold across the entire ecosystem right now. You've got electric hydrogen becoming the industry's first green unicorn with a $380 million raise to manufacture ultra-low-cost electrolyzers. You've got Australian companies like Hysata closing a $110 million Series B for next-generation designs. Add in companies like Coloma exploring geologic hydrogen and Zero Avia developing hydrogen-electric aviation, and you have a sector that has already amassed over $3.6 billion in equity funding. The capital is absolutely there, and the race to commercialize this tech is moving at lightning speed.
Section 4, atmospheric space mining. Okay, so if we can successfully pull valuable gases like hydrogen out of Earth's atmosphere to power our civilization, let's zoom all the way out and ask a truly wild question. Where else in our solar system is hydrogen just floating freely in the air?
The answer? The gas giants. Excluding our sun, the sheer volume of hydrogen and helium swirling around out there in the outer planets represents an unimaginably vast, untapped energy reserve. If humanity masters fusion power, which requires these exact elements, by the way, the atmospheric mining of these planets could deliver an energy return millions of times greater than the energy required to extract it. When you look at the atmospheric makeup of these planets, Saturn actually has the highest percentage of hydrogen, at over 96%. But Jupiter and Saturn have punishing gravity wells, extreme winds, and really tricky magnetospheres and rings to navigate. So scientists actually theorize that Uranus and Neptune might be the most suitable candidates for future atmospheric mining. They still boast over 80% hydrogen atmospheres, but they feature much smaller gravity wells. That makes it vastly easier to get spacecraft in and out of their atmospheres.
So how would we actually pull this off? Well, scientists have already mapped out some pretty wild proposed technologies. We're talking about robotic fleets of aerostats, which are buoyant floating gathering stations suspended deep in alien clouds. We have scoopers, which are vehicles that skim the upper atmosphere, capture gas, and bounce back to orbit. And perhaps most ambitiously, skyhooks, massive orbital space elevators that essentially drop a giant straw down into the atmosphere to pump gas directly to an orbital propellant depot. It's essentially creating the largest cosmic drive-through imaginable.
Finally, Section 5, our elemental future. Let's bring this all back down to Earth for a second. Whether it's an Australian desert or the rings of Saturn, the core mechanism of extracting the fuel we need directly from the air is rapidly shifting from science fiction to our imminent reality. What we're looking at here is a physical, multi-stacked, solar-powered direct air electrolysis tower operating outdoors right now, created by the team at RMIT. From this very real operating solar tower proving we can harvest clean energy from a dry wind today, to the theoretical skyhooks of tomorrow, our energy limitations are suddenly looking a whole lot less terrestrial. We are literally learning to use the ambient environment as our fuel source.
And that leaves us with one final thought to ponder today. For centuries, we have dug deep into the dirt to power our world. But as we look to a cleaner, post-fossil fuel future, is the ultimate wellspring of power simply waiting for us to reach out and grab it from the sky? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.